Okay, so you might ask, having looked at the two function block diagrams, ladder diagrams, there's no difference between the two. Why do we even bother with one or the other? Why certainly do we bother with ladder diagrams when we can do it much easier with function block diagrams? Well, I'm going to show you now one of the areas where it can be useful to have an understanding of ladder programming when you're working function block diagrams. And that is something called a ceiling switch. So what we're going to do is I'm going to set up going up here, and I'm going to convert to ladder. So we've got a ladder, and I'm going to produce a ceiling switch. Now a ceiling switch is actually critical to most things that we see in the production line technology these days. We don't really like big physical flicky switches that have to move a great deal of distance, and there's some resistance within them and they clunk across because they're prone to wear and tear. They're also a little bit harder work for operators to use, so if they've got an awful lot of switches to be flicking, it gets a bit tiresome and they forget things, and sometimes they don't flick them far enough and they don't latch into position. So we prefer little press buttons. Certainly you wouldn't like your keyboard to be made up of flick switches where you had to click it down and then click it back up again in order to produce a single letter. So we like little momentary press buttons. Now that's fine until you come to the problem of you want to use one to turn the machine on. What we want to be able to do is go in, press a button, the machine runs and we can walk away. We don't want to have to pay an operative to spend all day with their finger stuck on a button holding it down so that the machine works. So your ceiling circuit, and there's various different versions, I'm going to show you one of the simplest, is a fantastic way to make sure that once you press that button that the system stays running up until the point that somebody wants to physically turn it off. So first of all, you'll notice the instructions here have changed a little bit. So rather than just being input, we've got make contact and break contact, normally open, normally closed. Interestingly enough, Alan Bradbury terminology makes a normally open or make contact examine if closed, and the normally closed they call that examine if open. So you'll often see, if you're dealing with their particular programming systems, you'll see XIO and XIC for normally open and normally closed. So we're going to take a make contact and we're going to put that on our first line. Come on. And that's input 1. That's fine. We're going to take a break contact and we're going to put that there, and we'll call that input 2. And we're going to have an output coil. We're going to put that here. So initially let's just put some lines across to join these to there, to there, and to there. And we're going to put another make contact. We're going to put that there. Now this is where it becomes slightly different. So when we spoke in the beginning, we talked about there being external switches controlling relays, and the relay coil controlled its own contacts. That's what we're going to do here. So we're going to call this contact the same as this coil here. We're going to call that Q1. Now if we look, scroll down through the list, there's a lot of them, but eventually we get to Q1. So we click on that and we say OK, and now we can see, oh, didn't mean to do that. Now we can see that we have Q1 here and also Q1 here. Now this connects to the ladder, this connects in between these two inputs here. This in essence is a very, very simple seal-in circuit. So what happens, and we can look at this in a simulation, and what I'm going to do is I'm going to change these to momentary push buttons. So we momentarily push it to make it, and same with this one, momentarily push to make. So input 1 is our start button. If I press input 1, which is just a momentary push, and I just hold it down for a second, what you'll see, input 1 has become true. It's red. When I take my finger off, it's now false. However, what's happened is when this is true, logic can flow through, and it flows through to I2. Now because I2 is a normally closed kind of input, it's able to continue flowing through to the coil. Because this coil is true, it means that this contact down here, Q1, is also true. Now because this is true, logic can then flow from the ladder along this rung up to this branch here and then along. So now, even though I've taken my finger off I1, the start button, the circuit is still true, and it will remain true until I move my finger across to input 2 and press that. Because the moment I press input 2, that goes from being normally closed to being open, and now there's no possibility for the logic to flow through to Q1, which means Q1 contact down here is also false, and so therefore the circuit is switched off. It's really simple and it's effective. So we can just literally, with a press of a button, turn the whole system on and leave it running for as long as it needs to be. You can then put emergency stops in here. You can have multiple I2s dotted around the machine so that anybody can stop it at any given time. But it gives you that flexibility to have a momentary push button to get everything started. So we haven't really got much else happening here. All we have is we're energizing this output to make this contact closed to keep it running. But what we can also do is we can now insert underneath another line that's also a contact of Q1, and you can then get that to do something else. So let's turn the simulation off and I'll show you. So we're going to take another make contact. I'm going to put that there, and we're also going to call that Q1. And then we're going to have a relay coil here, which is Q2, and that's going to just be a light, but it could be an electric motor, it could be a conveyor belt, it doesn't matter. So we'll make the connections. Oh, right. That's not gonna work. Like so, and simulate it again. Now we've got two lights here. Remember, Q1 may not actually be a physical external light. That's just telling us that that coil is switching on. But Q2, we can imagine, is our motor. So when we turn on the input, as you see, both lights come on. So Q1, which can be entirely imaginary, just digital held within the PLC contactor, is closing this imaginary PLC contact here, which is turning on this external light, which is our motor drive, our production line, our conveyor belt, doesn't matter. So we can have multiples of this Q1 turning on 15, 20, 100 different things. Doesn't matter how many contacts you link to the relay coil. They can all be operated by that one coil. So you can see how this little seal-in circuit, which is worth memorizing, makes the control of operations really, really straightforward. We've now got a start button and we've got a stop button, and they work really effectively and really easily. Okay, so how does this influence what happens in function block diagrams? I've got rid of the second line, so we've just got our ceiling circuit. I've got rid of the simulator, and I'm going to convert this now to a function block diagram, and you'll see why it is worthwhile being aware of exactly how to produce things using ladder programming. So there you have exactly the same thing using function block diagrams, and as you can see, its complexity is much higher. So these two lines going straight up are actually linked along the top, although it doesn't show it. This is a continuous loop. We have, I'll hover over them so you can see the little pop-up boxes. We have our input 1 here, and that is flowing into an OR gate. That then flows into an AND gate, and the AND gate is connected to input 2, which then goes to the output. It is a much more complicated thing to draw up if you're not familiar with it. Sometimes when you're programming these things, even with function block diagrams, it is easier to start with the much simpler elements of a ladder program and then convert it across than trying to do it directly into function block diagrams. We can see if we load up the simulation, we have exactly the same thing happening. So if I press the momentary switch here, you can see, in fact if I hold it down, you can see the lines of logic flowing. So we have from the input, the logic is going to the OR gate here, which if I release, it stops coming from here, but it's flowing down this line and along here from Q. So that's giving us our locked in loop, and because it's an OR gate, it will accept either input and still become true and send the logic on to the next gate. Now the AND gate here requires 2 sets of true logic to be operative, but because this input 2 is a normally closed switch, it's actually getting that. Even though it's not highlighted as red, because it's normally closed, there is a flow of logic coming through here, which means because this AND gate is true, the output is therefore on, which feeds back into the circuit, and we have our continuous loop, which is keeping the setup running constantly. When we then press I2, it becomes true, even though in actual fact it's false, and it's switched off the whole circuit. Can be a little confusing with the function blocks when you've got normally open and normally closed contacts, but once you run through the simulation, you can see what it's doing. It's relatively straightforward to understand exactly what's taking place. Right, let's look at a practical application.